Assume the wheel is a disk, mass m, radius r, and it is on this ramp that is L long and is inclined theta. If you don't like any of that, I could put numbers there, but my preference is for you to figure out what is V when it makes it down here. And I'm saying from the very beginning that the disk rolls without slipping. That should be enough information for you to kind of work this out. And I'm just curious. If you just use conservation of energy, you can start with gravitational potential energy up here. And when it makes to the bottom, it'll have kinetic, but there'll be two kinds of kinetic because it's rolling. So the center of mass is moving, that's 1/2 mv squared. And it's spinning, so it's 1/2 I omega squared. Assuming it starts from rest, all of this energy will be converted to kinetic energy here. Now that should give you a good solid start. So if you're taking notes and you're stuck, this problem can be done more than one way. I've chosen a way, or at least I'm chosen to tell you the way I want you to do it. Conservation of energy is probably the easiest way to do it, but how do you know you can use conservation of energy? The biggest indicator is the mass makes a change in height. That's the biggest indicator that you can use conservation of energy. There are other indicators too, but as we try to determine what's the best way to attack a problem, we're looking for things that might help us narrow it down because there's going to be multiple ways to attack any problem. I'm choosing this one because conservation of energy is generally pretty straightforward. It has the least amount of kind of hard math associated with it. Usually generates one relationship, and from there you can solve for the variable of your choice. That's why conservation of energy is a good way to go. Can't always use it, but we can in this case. The object has gravitational potential energy. That's going to be mgh. But this is h, and I kind of see that that's the opposite side of a triangle. So I can use just a little bit of trig and know that that's going to be L sine theta. And so L sine theta, that's how much gravitational potential energy I have. Well, that's going to be equal to kinetic energy, of which there are two types. We're going to have translational kinetic energy and rotational kinetic energy. So you know those two types. 1/2 mv squared plus 1/2 I omega squared. The reason I know both of them have to be used here is because there's no fixed pivot point. The pivot point's moving. It's not fixed in place. If it were fixed in place, it would only have one of these. And if there was no rotation, then it would only have one of these. It has both, and because the word rolling has been used or invoked, we know one more thing, and that is that these two things are connected together by V equals omega times R. That's the leap I needed you to make today, that although you were told about last week, we never used it in practice till just now. Which means I can switch this from 1/2 mv squared plus 1/2 I, and instead of using omega, I'll use V over R. Now, in your notes, you might ask, well, why do that? Well, I asked for the linear velocity. And because I asked for the linear velocity, it's best to make my whole problem in terms of the linear velocity rather than the angular velocity. It's your knowledge that this is what's used for that that's important. But of course, we're not done yet. There's still more. if I want to make the problem something that takes into account rotation, I'm probably going to need to use the inertia of the disk. And that's right here. So you'll have to know the shape, and you'll have to know which moment of inertia to use. Since I said it was a disk, I'm telling you to use 1/2 mr squared for the disk. So that gives me 1/2 mv squared plus 1/2 mr squared times v squared over r squared. I just distributed the square. And that still equals mgl sine theta. In one of these conservation of energy problems, if this is all done correctly, one of the things you should notice is that the r's will sometimes cancel out, allowing you to combine both forms of energy. This is very common for things that roll, to have the radius not be part of your answer. So I have 1/2 mv squared plus 1/4 mv squared. That's going to be 3/4 mv squared. And that's still going to equal mgl sine theta. And just like first semester, it's very frequent. The mass will also cancel out. All right, so we did it once. Just to make sure you kind of got this, try it again for a ring. Just practice once. Let's replace this so that's not a disc, but is a ring. Okay. You're going to have to change this. Give it a try, please. If I just zoom to the end, just get the square root of GL sine theta. Is it clear which one of these is bigger? Not a surprise, right? We did this in class. I lifted up the edge of the table. The disk made it down first. The disk is faster. 4/3 GL sine theta as opposed to just 1 times GL sine theta. If you really want to make the comparison, you should also compare it to what happens if it doesn't roll and slides without friction. This is where the details become important. If it slides without friction, there is no using the kinetic energy for rotation because there's no change in its rotational rate. It just slides to the bottom. You should prove how fast it's going under those circumstances. And it shouldn't surprise you that when you do it, you're going to get the square root of 2GL sine theta. So it's faster still. And prove that to yourselves. Make sure you can do that. That's just dropping something. We've done that a bunch of times. That was all first semester. The first thing I want to point out is that it should be obvious to you that when you start changing the moment of inertia, you get different answers. That some objects will roll faster than others because some objects are easier to roll than others. Why is it that the disk and the ring both are slower than just sliding down the ramp? Well, because that total amount of energy has to be divided into 2 things now. It didn't before. If it was just a block sliding down the ramp, then all of its energy went right into translational kinetic energy. But now there's energy split into 2 parts. So it has to be going slower. Now, hear me out on this. If you can figure out the final velocity, then you can also figure out things like acceleration, because you can use a motion equation. These objects have a constant acceleration. So you could find the acceleration this way. Probably something like, v squared minus v naught squared equals 2a delta x would probably do it. Because delta x in this case is L. It went down the entire ramp. I don't want to repeat this kind of problem because this is just beating a dead horse. We've done this kind of stuff a while ago. But you could get or tease out different things. I'm telling you that this is important because we're about to talk about net force in a system like this. And net force is the harder way to do this problem. You're capable, but it's harder. And I have this whole thing that we've just done is like half of one of your homework questions. So if you looked at your homework, you know that this is like, you have to do this for a ring, a disc, a hollow ball, and a solid ball. So we've done half of it. Now do the hollow ball and the solid ball. This is the practice I want you to do. But there's something else that you need to be capable of doing. And I think this part is actually kind of hard. I'd like you to be able to determine the force of friction on an object that's rolling. And I've got this all over your homework on purpose because I find this to be a bit of a challenge. We started talking about it on Friday. Today, I kind of want to finish it up. And I know a lot of you were out on Friday. We still have to move forward. So on Friday, we identified the forces that act on an object. Today, we need to actually work the problem out. So in order to not waste your time, I want to be quick about getting the forces back out here in the way in which we did. I have a incline that is angled theta, and therefore there are 3 forces that act on it. We're going to assume that our object is at rest right now and is about to roll down a ramp, and that there is sufficient friction for it to roll. But we don't know the coefficient of friction, and it won't be in our answer. I want an expression for the size of the frictional force. All right? Now, to do this problem, I want to first not tell you what the shape is. It's just that it's round. So we're going to work a solution that has moment of inertia in it, and that's on purpose. So our object has mass m, has radius r, and moment of inertia I. But I don't know if it's a ball or a ring or what it is. If we do it this way, then you have something that is reusable, and you can put in whatever the moment of inertia is that you're given. So I want you to have a solution and see how it's done, but I also want you to see where each piece of the object's parameters shows up in the answer. So there are 3 forces that act on the object. The first is gravity. And on Friday, we talked about the fact that it's applying a force, and it could also be seen as applying a torque. The second force is the normal force. So I'll try to get it right there at the center. It's perpendicular to the surface, and it goes through the center. It does not apply a torque because of the direction upon which it acts. And then friction. Be careful when determining friction. You need to know whether the object is speeding up or slowing down, going up the ramp or down the ramp, or you can't answer this question. But that has always been true about friction, is that you have to know the direction the object is moving to know what the direction of friction is going to be. If this object is going down the ramp, then friction has to act up the ramp. Friction is doing one of 2 things, depending on how you think of it. Friction is either holding this place so the object doesn't slide across this point, or friction is causing the system to rotate. It really depends on how you think of the problem. You have to pick one way to conceive of this question. And you have to go from there. Because what we talked about on Friday is that I can choose either of these 2 places as my pivot point. The actual pivot point is here. And that's the proper place to do the problem. But you will get the right answer if you choose the middle of your object as its pivot point. I'm going to work the problem with the pivot point at the surface on purpose. Now, I'm not going to waste our time with net force stuff because we've done it before. We know how to do net force stuff. We talk about the net force in the x direction is going to be mg sine theta minus friction equals ma. Right? And in the y direction, although we will not use it, that's going to be something to be 0 because we are making our x and y aligned with the ramp. So normal equals mg cosine theta. Now, torque. When we're doing the net torque function, which is I alpha, our net torque is we have to evaluate every one of these forces to see if it causes a torque. Based on where my pivot point is, neither the normal force or the friction force apply a torque. Because based on where my pivot point is, the system has no torque arm for friction or for the normal force. However, mg sine theta is applying a torque. mg is a distance r away from the pivot point. It's a force size mg, and the angle between mg and r is not phi, is actually theta. So when I do my torque, which is supposed to be r times f times the sine of the angle, it's going to be capital R for the radius of my object times mg times the sine of theta for the ramp. The hard part is that I has to be the moment of inertia about this point. So you have to use the parallel axis theorem. That makes it kind of messy, but not terribly so. It's the moment of inertia about the center of mass plus mr squared because we are shifting it one radius. Now on Friday we did this for like a disk or something, so we just put in the moment of inertia. I'm intentionally leaving it out. Now, if we want to find the frictional force, yes, sir.
Wouldn't it be mg cosine theta?
Nope. Nope. The dot product is sine. We're doing the dot product here, and it has to be the angle between the force and the torque arm. So we are looking at how this force causes it to pivot about this point. And therefore, we have to use the angle between the torque arm, which is, sorry, let me back it all off. There. The torque arm is this distance right here. That's the torque arm. And then the force is this way. Okay? All right. Now, we're going to be close on time, so let's get to this last piece. I want to bring this and this together to solve for friction. I want friction by itself. So the only way to do that is to eliminate acceleration. So I'm just going to pull this off to the side and have mg sine theta minus friction equals ma. And because the object is rolling, I'm going to write this as r mg sine theta equals I center of mass plus mr squared times a over r. For something that's rolling, remember, we know this has to be true. And if that's true, then this one also has to be true. It's rolling, so I can count on that. Now, you may not know where to begin. I'm going to give you a place to begin. Do you notice that both of these have an mg sine theta in them? solve for mg sine theta, and then set those two things equal to each other. That's the way to do this. So mg sine theta equals friction plus ma. Actually, no, I don't want to do it that way. I'm sorry. I don't want to do it that way. It would work, but there's an easier way. We want to eliminate a between these. That would be better. Now, it still looks messy, but it'll only be messy for a minute. There. Now, the other one's going to be messier, but I'm just going to multiply both sides by the r's to make that r squared. And I'll get r squared mg sine theta over okay? Messy, I know, but we set these equal to each other, and then we just have algebra. What do you think is going on over there? I mean, now, this looks like a nightmare, but we want to solve this for f. I don't think it's terrible, but there's a lot of things to do to solve this for f. The easiest way to solve it for f would be just to multiply both sides by m, because that will get rid of it over here. It's messy, but follow me through, please. Multiply both sides by m. I get mg sine theta minus friction equals m squared r squared g sine theta over I center of mass plus mr squared. Guys, see all that okay? Now, I'm going to just regroup it. And mg sine theta is in that term, so I'm just kind of getting it by itself. Now, I want to get friction by itself, so add it to both sides. And then I want to get this over to the other side. So subtract all of that from the other side. Ugh, this is such a mess. Is it me or is it eerily quiet over there now? Is that worse? I think it's worse. Okay, so I know it won't make sense why I'm doing this straight off, but just try it for a minute. Factor out mg sine theta. Again, I know you won't understand why I'm doing this. I just want you to see it, okay? Get common denominators. Mr. Shelton, why? It's so messy. You see I got common denominators? Okay, just one more thing. Combine them together. Do you see how the MR squareds on top will cancel? And I get I over I plus MR squared.
Wouldn't it be easier if we had the actual center map, or like if we knew the shape?
It would, but there's something that we can't show with that. So I wanted to get here, and I'll explain why I wanted to get here tomorrow, because we're out of time. But this has some really important meaning, and you'll see it tomorrow.